years.
But his
Today is election day, but it's an off-year election. So,
No, that'd be nice.
No, I mean,
but-
like any city offices, school boards, levies. Yeah, so like next year. Hey, so this actually matters. Next year, Worthington will likely have a levy up, and we will really, really need to pass it.
What's the levy up?
So, like for vote, but a levy is like money that comes out of people's taxes or gets added to people's taxes to pay for things in the community, such as
So we're gonna get more
schools.
money.
Yes, because Worthington is still growing, and yet we cannot get any more money from the federal
Upper
government.
Arlington's better though. They have a better test.
Okay, sure, that's fine. That has nothing to do with us needing money.
They have a good mental sharp.
All right, so
Not fair.
It cost like $130.
we were looking. Should we sit down on the counter thing? We were looking at 446, trying to discover who stole my pencil sharpener. No, trying to discover some interesting patterns. So check out 446 again. Sorry, I think I just said 47. Check out 446 again. Look for what you might notice. So, like, we sorted the other ones.
Oh, wow.
We have gold rings. She has really good pencil sharpener. She has, like, the best in the school.
There is very
People, it used to come
Yes.
from different classes to sharpen their pencil. And does it work on this?
There's the number 2.
So, really, what I want you to compare is the difference between E and F. Their factored forms to something like B. So E and F yesterday, we talked a little bit about. Did we get to the point of factored forms for E and F? Okay, you said 3x plus 4 for both?
Wait, that one doesn't work.
Mm.
I forgot. I'm sorry, I'm a disappointment right now. Jenny. Yeah.
Jenny. Quit being hyperbolic.
Only at my own.
We'll throw in a math word there. Quit being hyperbolic. So 9x plus 4. Crap. Right.
Oh, yo, go and look up like you did to us. Please.
Only at my own.
Do it. Just be like, oh, I'm pretty sure this is older than you. No, don't stop, bad. You should be like, yeah, he did. He was like, psych. Oh my gosh. You didn't tell us though.
Calm down. There were like 6 of them.
See, Jenny thinks
I don't want to scare people. It's still November.
I don't
Look,
want
you're
to scare
remem-
people.
look,
Yeah,
You're remembering like February.
I don't
Yeah,
remember
that was
you yelling
scary.
that hard. So Jenny
Yes,
felt like
he was-
she's like, yeah.
No, he was
like, you
so-
yell at us.
Okay, it depends on which reading you're in because at points it gets like crazy loud all of a sudden. So, did we at least, while you were wanting me to yell at people, figure out F? So, Jenny, let's redeem yourself, right? 3x plus 10 and 3x minus 10. Now, what do we notice about the coefficients and constants compared, like, in the binomials compared to the coefficients? Ooh. So we've got square root relationships. Right? Because when I... Can you calm down? When I square something... I don't want to say too much. So what about like D? Because like 9's a perfect square, 4 is a perfect square. Did we have a factored form for D?
Yeah, 3x plus 4.
So if we just try to go with the square root, right? 4, we have to use 2's. Ah, the square roots, but make them negative. So try to figure out patterns here. You can't look at 47. Hey-yo!
She's so happy that she's not.
No.
Wow.
Wait, what?
Top.
Let go.
Don't step on me.
So that's interesting. That one, both your statement and this. So that one comes out to be a perfect square. So if I combine that, I'd have like 3x minus 2 squared. Okay, now that middle term is not a perfect square though.
Yeah, but the sum of the products of the two terms would be.
You are correct. I like how you said that, dude. The sum of the product of that was yeah. The outer and the inner terms, right, Chris?
Because of the non-perfect square, we know that the difference between the x values is going to be 5. I mean, yeah. The constant.
Are you talking about B?
Yeah.
Okay. So we got this one right. So B, you're saying because of this and this, so you're making the relationship that 36 is perfect square.
Yeah.
And 5 is most definitely not. Okay, so we have x and x because that's kind of my only option. So then repeat what you just said.
So that means the two constants have to have a difference of 5. That would be positive.
The constants we use here and here will have to differ by 5, but that's also because the coefficient of x squared is only 1, so that doesn't come into play. Okay, so then what are they?
4 and negative.
Yeah, that's what I got.
So that doesn't work. So wait, why did D work and B doesn't? And I'm not really looking for an answer. I just want you to kind of observe. See that nice whole, like, because I raised my hand, I get to talk.
Yeah, sorry.
Okay, so 5's prime. Good observation.
And there's no constant, no coefficient on the x.
Okay, no coefficient on the x.
5x is less than, or yeah, negative 5x is.
I like that you got your train started. You're like, I'm gonna do
I was
it.
gonna say that.
Guys, that's well, this is math too.
I was gonna say that 5x. I was gonna say that 5 is less than 36 and 12 is more than 4, but then I realized negative.
Yeah, negative, right? So let's look at 47, because we got to move on at some point. So if you notice, 47 specifically hones in on 9x squared minus 100. And as we've already said, both are perfect squares, 9 and the 100. Obviously, the minus we then look at as minus, not negative, and it's arithmetic. So a quadratic expression in the form u squared minus w squared is a difference of squares, as we've talked about for a moment 2 days ago, I think maybe, where we know because that subtraction in there, one of the terms has to be negative. And actually, when we break apart that u squared, if there's any coefficient to the x, or the x squared, sorry, I should specifically say, that's going to get split by its square root, and then we just place those just like the 2x, 2x. When we have u squared plus, this is what we were trying to get at, that Jenny almost formally said. She said the sum of the products, which yes, that's true, but the products, outer and inner, have to be the same, because what we're really doing is doubling the product.
Of the sum of the products of the term.
You are correct, yes. I'm not saying you're wrong, you just didn't get all the way to saying we actually just double it. I didn't say you were wrong.
I said you said wrong.
It's really fine, it makes me laugh. I'd much rather take those stories home than some of the other ones I have.
Wait,
So, this is angels singing, lights from above. Oh, I gotta put my pen back on. This is a perfect square trinomial, right? Perfect square trinomial. What you're looking for here is if your x squared has a coefficient and it's a perfect square, and your constant is a perfect square, process their square roots in your head real quick, multiply them, and double that should be the middle term. This will make more sense when we play with it and do
wait,
it.
so is it? But 3
Wait.
times 4 is not 24.
So, square root,
Okay.
square root, square root. Are you guys broken? 3, thank you. Square root,
4.
product,
12.
double,
4. Thank you.
Good. I just didn't appreciate it.
So this goes back to our closed sets. So this shows me that we have, well, I should probably ask the question. So we talked about polynomials being closed, or sorry, we talked about integers being closed, right, under certain conditions. Multiplication, it is closed. Division, not necessarily. So it's not closed. We remember this, yes? Closed means we'll get out the same sort of thing we put in, right? So when integers are closed under multiplication, multiply 2 integers, you will always get an integer. Division, not the case. Now, rational numbers, we could look at differently because a rational, will it make a rational? But that's not actually where we're going today. Polynomials, right? What we've been working with. Those binomials, trinomials, are they closed? So take a minute to talk with your team. Are polynomials closed under addition? Think about what we're using polynomials to represent, or what represents a polynomial. Think about what would happen if you add 2 of them. Play out both options even. Any multi-termed expression. So a monomial would be like 12, or 12x. But a binomial would be 12x plus 2, which is a polynomial. Poly, many, right?
Polytheistic? Negative 1
I'm not very
2
talking
and
about
then
this.
1x. You don't need to check that. Yeah.
Grades up in really have
Okay. Yeah.
Oh, by the way, this is actually worth showing. I didn't realize that the digital text didn't have it in here. And it's only in the, I guess I'm going to have to go. So check this out. The reason that the perfect square trinomials and the difference of squares trinomial work out how they do, where we wanted to get to that double point, is from the area model. So just to make sure that we see that, since we have this focus on modeling, So I was just glancing down my book and I realized, like, I thought that was part of the book. I guess it was part of the teacher text. So here's our difference of squares. These will cancel out, but they are both UW. Just one's positive, one's negative. Here's our perfect square trinomial, because they're the same, and instead of canceling out, they double, because they're both identical. So if you wanted to visually justify that, that would be how we can show it with an area model. Any questions with that? I just want to make sure you saw that, because honestly, a lot of this stuff, how CPM teaches slightly different than other courses, is really cool. Like, I now have a better understanding of this stuff than I ever have. So that is how we would visually show that. In addition, anyone have hypotheses yet? What do you think?
Of what?
Yes, no? Whether it's closed?
I say it's not closed.
You say it's not closed?
Under attention.
We're going to give you a couple more minutes to talk. Because nobody else really spoke up, so I'd like you guys to process your ideas a bit more.
But like, subtracting this from that, one x
A polynomial doesn't know what x is. Otherwise, it would be a monomial. Come on, Chris, use your roots, or whatever you just said. No, that is funny. That means polynomial. What have we been using to represent polynomials? Not quite. Okay. Areas, right? Physical values. So I'm going to pose a couple questions here. Give me, if you think it's closed, addition. If you think it's closed, give me a thumbs up. If you think it's not closed, give me a thumbs down. If you don't know, give me a sign. Closed, not closed, I don't know. Closed? Don't know.
We're like iffy. Middle. We think it is, but we're iffy.
So let's back up. I want to really make sure we have a solid foundation. I'm not going to give you the answer yet. Polynomials. When we look at those trinomials, what was the difference between one that makes a rectangle and one that can't perfectly make a rectangle? What was the difference between one that we could perfectly show with an area model rectangle and one that didn't quite work? Was one that didn't quite work not a polynomial? It was still a polynomial, right? And it just
all of the terms were binomial.
like if I make up, let's see if I can make one that yeah. Is that polynomial?
Yeah.
Could we represent that with tiles? Could we make it with a rectangle?
Possibly. Give us some area all the time.
Think this out. You got to start to visualize it in your head. If you have an
rectangle.
x squared,
Yeah, that would work as a rectangle.
x, 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 right? So that, and then my 2. That'll work.
But not +3.
What if I make that 3? Is it still a polynomial?
It's still polynomial. It's just-
Could I still build it with tiles?
No.
Yeah.
Any
No.
number
besides
Oh, yeah.
that.
Oh, yeah.
I could still build it, right?
Number 4. 4.
What's the difference between the first polynomial and the second?
His two prime.
What can't I do with this? Which means I can't what? Factor it. At least easily, with what we know how to work with, right? With the integers and the things we... This is not factorable, at least under the conditions that we know right now. But it's still a polynomial, right? So what if I took, we'll go back to the easier one, the x squared plus 3x plus 2, and did another x squared plus 3x plus 2. Can I add those together?
Yeah.
Do I get a polynomial?
Yeah.
would that polynomial be factorable?
Yeah.
Does it matter if it's factorable for if it's a polynomial or not? So what do we think? Is it closed or not? It is closed.
I was right, but what if you have like
Hold on. Yeah. What?
what if you have like the numbers that cancel out?
Would you like? Okay. I love your questions. I always love your questions. So what if this was negative?
What if all of them were? No, and
Negative x squared minus 3x minus 2 is what technically saying.
Okay.
then you just have x squared.
Oh, so you want the x squared left? You want an x squared left, or do you want anything left?
Everything's negative, so it cancels out completely.
And it makes 0. And that's a mononomial.
Then it's just
Isn't
That's
it?
just 0.
Yeah.
0 is the mononomial.
So-
But
but subtraction.
Is a prime number still a number?
yeah, of course, everything's a number.
Actually,
What?
Every number is a number.
Actually, Ryan, if
Is
you
a
add it,
is a
Everything's a
binomial a
number.
polynomial?
Yeah.
Is a trinomial a
Right.
polynomial?
Actually, it's adding and then
But
Is
it's
a
a
monomial a polynomial?
It
is
Oh,
addition.
wow.
Is one a number?
It is
Yeah.
actually.
Yes.
Yeah, but it's not more than
So, yeah.
More than one.
Poly, if we're being literal, right, means many. But, I mean, come on. We could say there are 0 of these, 0 of those. I like your argument. I really do.
It's a polynomial.
But we're still getting back a value of a certain amount of terms, which these terms we can really just represent with these tiles. Whether or not it's factorable doesn't matter for if we're just talking about if it's polynomial, right? So if you think of just, we're just adding like terms. Any polynomials can be put together and just add like terms. Now, I love the argument, what if they cancel out and then we end up with nothing?
0x squared plus.
But really, I think their argument would be, we're talking about addition. You'd really kind of be arguing subtraction.
Yeah.
They should. Now,
Is that a me or
calm down.
Adding and then
For both addition and subtraction, we do classify the result as a polynomial. So I don't know exactly what you were laughing at, but we will say that yes, this is closed under arithmetic. Polynomials as a set are closed under arithmetic. All right, let's jump to our next lesson with only 20 minutes. to go. It is great. So we are totally switching gears.
Yeah,
So-
like completely.
To teach you a little bit before you need to know it, everybody take your left foot, push in the clutch, take your gear shifter, and move from one gear to we are shifting gears.
I thought you said literally, and I was like.
Then carefully release the clutch while you push the gas in, otherwise you will stall your engine.
So.
That's clutch.
Did you say you want a calculator?
Yes.
Too bad.
I'm gonna calculate it too. That's so cool.
Well, good thing Christmas is soon. So,
My grades are bad, but I'm gonna be able to. They did that. They could buy me.
Yeah, look, I can actually see the screen now.
Wait, what happened to it? Did you get
Dead batteries.
were dead.
So, let's focus. 4.2.1. If we were to travel to San Francisco, I just went out to California last year for a wedding. It's a cool place. You should go if you get a chance. San Francisco is notoriously known for its very steep streets, and because of that, its trolley system. Right, so the trolley system there is very sweet. If you got there, you should drive the trolley. But if you went to San Francisco and you took a hike, you'd get very tired very quickly. Just like, what's her name? Janisha. Who?
Juanita.
Juanisha. Stop. You're setting a bad example. I try to get my 7th graders to stop doing this.
What?
So, Juanisha has only climbed 100 feet, right? Her Fitbit tells her, I've walked 100 feet. She stops to take a break. The hill she's on is Filbert Street. Filbert Street in the guidebooks will tell you it has an angle of 31.5 degrees, which means, come on, straight up is 90. So, like, that's insane for a city street where houses are built. So,
That's like that.
yeah, well, at the end of class, I'll look up some pictures of Filbert Street. So, what do you think? Juanisha wants to know, how far have I climbed vertically? Right? She wants to know how far she's gone vertically. Don't put those down. Can we solve this without a calculator?
I mean,
Now, you may pull out your resource page from the previous chapter where we had all those different triangles and the ratios.
But those are
no
hand
hand
ratios.
It doesn't have 31 points.
It was his shirt.
No mix, thank you.
Like, stop saying mix.
No mix, thank you.
Wait, Jenny, if you
I
were
could
McDonald's
say that.
and still say that, would you ask
My
for a
dad, my
Big
grandpa
Nugget?
still calls it Mix.
Yeah,
Okay.
What sort of information do you have on that sheet?
The ratios,
Ratios of what?
the size, like y over x, of y over both sides.
Ah, so we have rise and run, right? We have like slope ratios. We were making slope, really. Okay, so what triangle on there will help us here?
That's the one that's closest to 31.5.
What do we have? What,
68.
why would 68?
Oh wait, no.
It's
This is
really
all
good.
It'd be 99. Right? 60 plus 30 already makes 90. Wait, 58?
Yeah.
58 and a half could work.
What about like 90?
You're 55.
Come on, what hypotenuse is
We have
it?
89, 100.
Well, on your paper. What do we?
Oh wait, no.
I love those, like, every mathematician ever does that. They're like, wait,
I saw this.
I do that like every day.
I thought it was a 3-4 flash triangle, and I'm like, maybe? What?
make an isosceles triangle?
I don't know.
At least you're on there.
I mean, can we do this? What sort of info do we have? You're like really upset at me.
Hey, we can use the Pythagorean theorem.
X squared plus y squared equals
Okay.
all equals. All equals.
And that, or,
Because we don't know the ratio.
Equals
So we
10,000.
can't just calculate the Pythagorean theorem.
Alright, so it seems as if this is going to be really tough if we can even make a guess.
Well, that's where you
I got it.
tangent.
I got it. I just started.
Well, but that's all that we have.
80 and 60.
80 and 60.
Can I go to, okay, so can you explain this one? How we could use the Pythagorean theorem?
Me?
So could I? Yeah.
80 and 60.
I'm thinking. I'm thinking that if you so tangent of an angle is according to the trigonometry sheet. Tangent of an angle is equal to delta over delta x or slope.
So we know,
Slope ratio. So and we know.
in this case, if I go ahead and write it specifically, tangent of an angle equals what?
Delta x.
Y over x, because it's slope, rise over run.
And we know that the Pythagorean theorem is a squared has b squared equals c squared. Let's let a squared be delta y, b squared or not b squared. A be delta y, b be delta x, and c be 100.
Okay. How are you going to make certain that it has the right angle? Pythagorean has nothing to do with angles.
But one thinking is you have the slope ratio. You know what the slope is. And you use calculator. I think if you use some with a little bit of experimentation, you can get the right combination because you're squaring those and then adding them together, they have to equal 100 squared.
I agree. But
So
that
then
won't
we don't-
necessarily keep the angle. We'd have to be really precise.
Yeah.
So, Jenny keeps saying use a calculator. What's the tangent of 31.5? Go ahead, calculate. Tangent.
Calculator.
Oh my gosh.
Jenny, then get one.
That's okay, I'll have my.
Jenny, go right here.
It's 0.617.
You could probably reach with a
That's a number.
lead. What is it?
0.612.
Hey, we're like making noises? Come on, guys. Yeah, what? So, 0.61208, you said?
28. Not 0.
What?
0.6128007788.
So, approximately 6/10.
Yeah.
Okay.
Does that mean that the ratio is 6 times?
That doesn't mean that kind of helps.
I still say that we can't figure this out.
I mean, if I try to play through Collins' method of, then let's just say, okay, so 6 squared plus 10 squared, well, that's already too big. 36 plus 100, that'd give, no, I guess, because I have to square root that.
We should use sine.
Sine. I don't think we're supposed to know what sine is at this point.
What's the square root of 136? What's the square root of 136? Somebody help me out.
Wait, you want square root of 136?
Yeah.
18,496.
Square root.
Oh, square. That's
Square.
Root 34.
11.6.
11.6?
11.7.
11.66. So what we have right now with a really approximate triangle, and we could have actually done better with these, is if my legs were 6 and 10, it'd be close to that angle, which would be close to a hypotenuse of 11.6. How in the world do I relate that with my hundreds and doing it?
Well,
What if the 100 is C squared? Not C.
No, we can't do that.
Which one's the 10 and which one's the 6?
well,
Got it.
What do you think we can do? What do you think you can do?
If you divide 100 by 11.66, you can
Why?
get the you can just dilate it to get the
If we're going to do the same thing that we did with our tangent ratios, we know that once we set up a small triangle that is right, that has the same angles, you can dilate it out. So if we do 100 divided by 11.6, what do you get? 8.57, right? So that then would be our scale factor. Now remember, we're really approximate right now. But that would be our scale factor. If we multiply these approximate values up, what do you get?
The y would be 51.458.
And x?
I didn't do it. 85.78.
Do 85.7 or 78 squared plus 51.4 squared. Try it out. See how close we get. Should be about 10,000, right?
Yep.
Yeah.
You want to know what's really cool? Here's what the book says for the answer to this question. No. Since we do not know delta x or y, we can't find the tangent ratio.
So we actually can, but they're simplifying.
Oh, this is, I used to go rogue for everything. So I don't blindly follow. Now, we're really approximate. We would never want to do anything like this in like a lab type setting or anything. But using the things that we know, the approximate values that we have, and our information and our tools, we did use our calculator to find the tangent ratio of 31.5. But once we had that, we were able to do some approximate math and get there. Okay, now a couple times you guys said, well, I think we need cosine, or I think we need sine.
What is that?
So,
All three at the same
1 inch.
We supposedly need to know more, right? Our more that we ended up telling ourselves was that tangent ratio. But here, they've changed our triangle. Right, so they say use two different strategies to determine the delta y, the rise, for these slope triangles at the right. So take a moment, try these out. I think you guys have done pretty quickly, probably.
It's called a stage whisper.
Oh, here. I knew there was no erasers in there. What do we figure out here? So they say calculate the ratio of the change in x to the hypotenuse.
1 over
1.
How do we know this? Our rises
No.
from part A. How can we do it?
X squared plus 1 squared equals 2 squared. 4 plus 5 equals, wait, what?
Well, you can't. Yeah, you could say that 1 squared plus, y squared equals 4. But then the problem is y squared's gonna be 3.
Yeah.
Radical 3.
That is not
Hey, it's accurate.
Radical
about is accurate.
Oh wait, isn't it? Yeah, because it's like the 60-90 triangle thing, right?
Oh yeah,
30 triangle.
30,
60-90 triangle.
This triangle involves some very special relationships
Oh yeah.
because the 30, 60, 90 can be copied beside itself and then create an equilateral triangle. So what we now see is the height is root 3. Root 3, what relationship maybe?
I'm completely lost right now.
So we did this, right, for the little triangle. We said x squared plus y squared equals
Yeah,
Yeah.
okay.
1. This has to be 3, right? But square root of that to get y, my y has to be radical 3. You with me? But it can't just always be radical 3, right? So if I did like 3 squared plus y squared
Wait, for the
equals 36.
bigger one, would it just be 3 times radical 3? The big one. That'd be radical 27.
Y squared gets to, so 3 squared is 9, right? If we subtract 9 away, we get 27. Radical 27 becomes.
I just did that because I.
So what are we noticing here then?
I just saw that 2 times 3 is 6.
Okay, so we're going to say this.
Well, that arrow's perfect.
Thing.
Well, not quite.
So we're saying radical 3 times the short leg. Long leg is radical 3 times short leg. That's what we're hypothesizing. Right, yeah, I mean that it looks like that's holding true. What about the delta x compared to the hypotenuse? What ratio is that? You got?
What happened?
Because you're sitting there flipping your pen like you're like totally bored. This holds a 1/2. So how do we use that to solve the unknowns in part C? How does delta x compare to the hypotenuse? It's half. So then BC has to be 3.5, and AC then has to be
3.5 times radical 3.
that short leg times radical 3, because now we know that that ratio is going to, all we're doing is dilating here, right? If this is our reference side, then we can call that our unit triangle for this situation.
But that's not half.
What do you mean what's not half? The short leg is half the hypotenuse. That's the long leg. The long legs up here were becoming the radical 3 times the short leg.
Okay, so it's the short leg times radical 3.
Because if we look at this triangle, I hope we're with us. This is going to make everything later this year make more sense. That's our unit triangle in this situation because we're referencing the 1, right? So it's 1 unit. If I triple, I just dilate up, I just triple everything. Triple the hypotenuse, triple that rad 3. So if I go up and make my hypotenuse 7, then it has gotten multiplied by 3.5. So everything gets multiplied by 3.5. Cool? So, interesting. Let's move on and see if we can use this for anything useful. I have like 2 minutes clear, not captured. Or I have time to fight with my smartboard. One or the other. Alright, check out 48. 50, I can't see the first number. Alright, we're really out of time to start talking about this even because I don't want to take more time. We've gone over a couple days. So let's pack up. We'll dive in here. You guys already know more than what we know in this lesson, quote unquote, right? Because I won't let you use sine and cosine right now. So go ahead and approach your homework knowing what you know, using what you want to use, and we'll hopefully breeze through this a bit quicker tomorrow, and at some point catch up to finishing a lesson at the end of class.
I need to come talk to you during extension. That's kind of me.
I have math counts today, so you can come to math counts. I mean, if you want to talk to me, come to math counts. Like, you don't